Financial Modeling, Topic 8, Financial Planning Models, Section 4, Understanding the Macro Simulation Personal Financial Model. So in the first three sections, we talked about this personal financial model in which we build up money pre-retirement and start withdrawing money post-retirement to smooth consumption. I'm going to take that exact model and I'm just going to replace this static portfolio with a simulated portfolio. How am I going to do that? Is I'm going to take the prior balance times 1 plus the mean, which is exactly the formula here. However, I'm going to make this a random model. And I'm going to say plus a random variable z, which is a standard normal random number, times the standard deviation of the portfolios. In other words, you're going to have a random shock every year based on the standard deviation of the portfolio, which is based on the correlations of my asset classes and my volatilities and my weights. And so I'm going to basically get a random portfolio value every year. So let's go to the spreadsheet. Notice here's my portfolio balance times 1 plus the mean plus a contribution. And I'm going to turn that into 1 plus the mean plus random number, which is norm S inverse rand, which is Excel's approximation of a standard normal random variable, times the standard deviation of that year's portfolio. So now I'll look down here. Now every time I hit F9, I'm going to get a different number for the norm S inverse rand. So every time I hit F9, I get a new random number, which means just the basic gyrations of the capital markets. And what you see is every time I hit F9, if I go down to age 65, which right here, every time I hit F9, I get a new portfolio value, which is one possible lifetime of savings. I have a little lookup function here. And that lookup function tells me that every time I hit F9, here's the macro simulation to the right here. Every time I hit F9, it's looking at the number at retirement. So here's the $830,000. Notice there's the $830,000. So this is one single iteration or lifetime based on the randomness of the markets. So if I hit F9, here's a world in which I retired on 3.5 nominal, 1.5 real, and I had enough money to last 143 years. Here's a situation actually where my money ran out at age 80, or I'm sorry, portfolio ran out at money of age 89, and I wound up having 3 years of shortfall. Let's talk about one other thing this model does. Let's look at lifetime. This is the age in which you die. I have a formula in here that calculates the expected lifespan, 85 years, plus a random variable times the standard deviation. So every time I hit F9, that's a different year in which I died. 81, F9, 89, 82, 81, 82, 89, and so on. There's 102. That was a good lifespan. So every time I hit F9, I get a different age of death. Every time I hit F9, it tells me how many years my portfolio lasted. Let's assume these two variables are uncorrelated. And here it tells me, in this scenario, I died at 86. My portfolio lasted till 97. I had 11 extra years of money. Let's find, oh, here's a terrible case. I wound up living a long time, age 95, which is great. However, I must have had a lot of negative random shocks in the market. My portfolio ran out of money at 74. Therefore, I had 21 years unfunded. In other words, a shortfall in 21 years of just living on Social Security. So this is the basic stochastic model, in other words, random model of my portfolio returns and my life. Here's a scenario where it's just perfect. I lived to 86, not in pretty long life, and my portfolio lasted exactly 86 years too. So what I do to run the Monte Carlo simulation, I already have a financial model. I have my randomness built in, my my variable on age, and then my, each year there's a variable here on the market. that's uncorrelated with other years. So what I want to do is actually basically hit F9 and then copy for 5,000 scenarios. Copy this portfolio value, this nominal portfolio value, to give you an idea how much I retired on. It'll copy the year in which I died, and then copy my portfolio life and tell me how many unfunded years. So basically, take these last few numbers, copy them here, recalc, copy them here, recalc, copy them here, and then we'll look at this distribution and see, well, what percentage of the time did I actually run out of money? Now to do this, I could actually hit F9 and copy paste these values 5,000 times. However, what I'm going to do is I'm going to run a macro. Notice I have a thing right here, run simulation, on this art object, and it's assigned to a macro. The macro looks like this. It's called Sims 1000. But let's go look at it in the PowerPoint. The Sims 1000 macro is right here. Notice you start all macros with the word sub, and then give it a name. I called it Sims 1000, open, close bracket. And now here's the program ending right here, end sub. So here's what this macro does. To get the macro to run faster, I actually turn off automatic recalculation. So this is the VBA code to turn off automatic calculation. I then do a loop. For I equal 1 to 5,000, next I. So these statements here get executed 5,000 times. Cells 16, 14 equals 5,000 minus I. So cells 16, 14, 16th row, 14th column is this cell here. Notice when I run this macro, I take a few seconds here, it'll start doing a countdown of 5,000 minus I in this space right here. Should start any minute here. Well, while that's starting, I'll talk a little bit more. So let's go back. That's going to start doing a countdown in cells 16, 14. And then in cells 8, 20 plus I, 16, it's going to put whatever's in cell 8, 16 and 20 plus I, 17. Now I, again, I is going to go from 1 to 2 to 3 to 4 down to 5,000. So in cell 21, 16, it's going to put whatever's in 8, 16. When the loop goes around, it's going to put it into 20 plus 2, or 22, 16. So it's going to put whatever's in 8, 16, it's going to put it in the 21st row, down 5,000 rows to in the 16th column, 17th column, 18th column, and 19th column. Then I do a recalc. Now here's why I turned automatic recalc off. This program is going to run really slow because every time you do any operation, a cells operation in Excel, in a macro, it's going to do an automatic recalc and recalc your entire spreadsheet. But what I do is I turn off recalc. I do a countdown. I then copy all my values into columns 16, 17, 18, and 19. Then I do a recalc. Therefore, all these numbers in these cells get updated at this point, and then I start copying again. Then, after the loop is all done, I turn back on automatic recalc so your spreadsheet's all set. So let's go back and see if up here we're running now. So notice, here's what's happening. Here's the countdown. For I equal 1 to 1 to 5,000, for I equal 1 to 5,000, next I, it's putting in the, I thought that was the 16th row and 14th column. It's going to put in 5,000 minus I. It's then taking the values from here, this cell reference, which looks like 816, 8th row, 16th column, and it's going to put it here, then here, then here. Now it's also going to grab the portfolio death and put it here, and so on. And it's also going to do the shortfall off to the right. So each one of these 5,000 rows are going to be the nominal portfolio value, my portfolio death, my death, and the number of years in which I had a shortfall. Now, negative is a good thing. That means I had negative shortfall years. When this is all done, I'll then have 5,000 possible lifetimes. And then based on that, I can calculate things like the percentage of time in which I ran out of money, or what was my 5% lowest or 5% highest portfolio value. So we'll let this finish. By the way, a little hint here, if you don't want to wait for it to finish, you can hit escape a couple times and the macro will stop. But we'll let this finish and we'll look at these 5,000 portfolio values. You can see my first 5 possible lifetimes, $3.5 million, which is, again, a little bit higher than the average of 2.7. 1.7 million, a little bit less. 1.8, a little bit less. 1.1, a little bit. 2.9 is a little bit more than average. So, all right, so now we're all done. I now have 5,000 possible lifetimes here. I then calculate what was the average of my portfolio values. My average portfolio values is $2.7 million, which is about the same as the static, and that's as expected. The average is going to be roughly my static value. I then back into the real by discounting by the inflation rate. My average portfolio death year, 111, about the same as this. My average lifetime, 85 years. And then it calculates about the same number of shortfall years. Let's make sure I didn't change any assumptions over here. Looks like everything looks good. I then can calculate, well, what was the 5% smallest? If I sorted the 5,000 portfolio values, and I took the 5% smallest, that's 5% smallest in this column is $1 million. The 5% largest, using the large function, is $5.9 million. So now I'm getting more information than a static number. The static number says, yes, I expect to have about 2.7 million dollars. However, my 5% lowest is having $1 million and 5% highest is having $5.9 million. Then here's the important statistic for this entire Monte Carlo simulation. I'm going to count the number of years in which I had ran out of, or I didn't run out of money. So I'm going to count the number of years in which this is less than 0. And that's 76% of the time I have negative unfunded years. So 76% of the time I have enough money for my entire lifetime based on the consumption smoothing model. So we can kind of talk about this as our confidence interval. I'm 76% confident that given all of these assumptions and the gyrations of the market, I'm 76% confident that my portfolio will have enough money. So that's the key statistic and why we need to look at a simulation and not just a static deterministic model. The static model says I'm going to be fine for the rest of my life, actually 109 years. However, in reality, I only have a 75 or 76% chance or probability that I'll have enough money. So this is the macro simulation model and results. And the next topic, we'll just use the at-risk software to replicate those results and get some other insights.